Hello, welcome to the first session in complex analysis. So, the point is from where this complex number exists, or from where this complex number came out to the existence. So, the first one was traced back to 1st century BC. So, it was 1st century, not BC, AD. Here, traced to Heron of Alexandria. Alright, so it was traced back there. They were interested in finding the negative square root of negative number. For example, the solution, this x square solution of this, where m is an integer. So they were interested in this. So, yeah, and the next things what comes up is after around 1400 years. So this was quadratic equation. The solution of quadratic equation known since 6th century BC by Sridharacharya. Of course, it seems he did not mention anything about complex number. Though things make sense. So people knew around, let's say, 1600, around 14 or 1500, 15th century. Or 16th century, around this time. So the solution to quadratic equation were known. Yeah, of course, this was not formalized as the complex number. This did not came up that time, but people knew some expression. So if they want to find a real root, they can find. But around the same time, 16th century, Cardano Tartaglia. This is few other Italian mathematicians who wanted to find the solution of cubic equation, right? So, for example, x squared, x cubed plus ax squared plus bx plus c equal to 0, where a, b, c are real numbers. Of course, they didn't want to find any complex solutions or anything. People were not interested in complex numbers, but they want to find some real solution. And of course, one would expect there should be at least some cases there should be. Now we know there will always exist one real solution. So Cardano actually gave a method. Cardano provided a method for solving cubic equation like this. So, but he realized that you cannot avoid complex numbers even if you want to if you are interested in real solutions only. So then he got convinced. Though this was not formalized, the complex numbers or whatever things, they are not formalized that time, but he got convinced that those are useful even to find real solution. And that's how it began. And so this was around 17th century, 1637 precisely, René Descartes coins the term imaginary. Still, people were not convinced about the usefulness of complex numbers. But yeah, people are getting in the process of getting convinced. So Descartes coined the term imaginary. Then it comes to Euler, 18th century. Euler. He made really huge contribution in the popularization of complex analysis, or not complex analysis, actually complex numbers. Especially the formula e to the power ix equal to cos x plus I sin x. So this formula plays a very important role in the development of complex function theory in the beginning era. So Euler found this, and before that De Moivre proved his theorem, which everybody knows about from school. Now Euler gives a proof in 2 lines to the De Moivre theorem. So this exponential, the relation between exponential and the trigonometric function in terms of complex number becomes vital. Euler kept on exploring this to prove the trigonometric identities, which were difficult to prove at that time using real methods. So that's how it gained the popularity. Of course, no analysis was done that time. It comes afterwards. So 18th century Euler, and then Gauss also got convinced that complex numbers are important. Yeah, so complex analysis comes into existence in 19th century. The first one to start is Cauchy. So the real differentiation and the integration was there. Of course, not in the precise form, but was there. People knew. Now Cauchy actually wanted to develop an integration theory in the domain of complex plane. Well, then he found an analogous way to define a differentiability exploiting the field structure of complex numbers. For example, if you have a function, so first one is Cauchy around, let's say, 1820s. So if you have a function f from C, domain in C to C, and A belongs to C, and you can look at the same limit, right? F of A plus H minus Fa by H, and you take the limit as H tends to 0, H is now in complex number. So Cauchy looked at this quotient, and this is just analogous to real functions over R. Now he would say that this is differentiable, complex differentiable, if this limit exists. So if this C differentiable at A, if this limit exists. Well, this is good. This comes when he was trying to define integration or trying to develop a theory of integration, complex integration. Well, this is a nice thing. That's how it started. And he keeps on developing things through this process, and then he found his famous Cauchy integral formula, and he found certain representations of those functions, and so on. Now this is the approach Cauchy took. There are three approaches to complex analysis at present. One is, of course, due to Cauchy. Second is due to Riemann, 1850s. So he based the function to their geometric properties, and in the basis of them lies a differential equation, partial differential equation. So he took the function from the domain omega to C, this is in C, and he looked at f to be u plus iv, and he looked at this, if this is differentiable and you want this to be satisfied, this del u by del x is equal to del v by del y, del u by del y equal to minus del v by del x. So this system of PDE, partial differential equations, to be satisfied, and he emphasized that this is the foundation of the theory of complex functions, and of course it really is. And this is how actually the geometric viewpoint of complex analysis got developed. Around the same time, there was one other great guy, Weierstrass. Around the same time, 1850s, though his manuscript got published much later, but around the same time he was looking at the actual analysis, that he got part of it. So before that, continuity was not defined properly. He was the one who incorporated epsilon delta method to continuity, convergence, uniform convergence. He made things precise. Before that, so and he based his theory on power series. Of course, people knew about power series even before the Weierstrass, but Cauchy found the expression for those functions as power series. Riemann also used his power series in certain extent, but he was actually focused on power series and developed the theory. He made the precise, the issue of convergence was not resolved until his time. So he was the one who incorporated uniform convergence to it. And based on power series, he developed his theory. This is of course very crucial, and this is also very analogous to what happens in real life. So for example, if you have a power series in x minus x naught or n on R, Correspondingly, you can have path series in z minus x naught n on C. Well, the point is here, if this is x naught and this is the radius of convergence, if this path series converges here, then this path series will converge here. So very analogous to real theory. And this is also very analogous. This was certain, which is a little bit different from this two. Of course, we will explore all of three, and we will see those three approaches are equivalent. This is the first thing what we would like to do in this course, and after that we'll study and along the way we'll study the properties of those functions which are here C differentiable on an open set. Here it satisfies these equations. All those will be same, and how this there are some properties which are very interesting and very rigid. For example, there are no bounded C differentiable function on C which is non-constant. So every bounded C differentiable function on C will be constant. Zero set of those functions will be isolated. So there are very, very interesting properties. Although the set of such functions are huge, they're not very small. Okay, so and then we'll study the properties of domain up to certain equivalence in this sense, in this category. Just like in the case of continuity, you have the homeomorphism. In the case of differentiable functions, you have this diffeomorphism, whatever that means. Similarly, here there are some things. So under those, we will study some domains, and some explicit maps which we will also would want to study. For example, exponential, logarithm, polynomial, and then some certain simple rational functions. Those which have very nice properties. Okay, stay tuned, we'll see more.